Hello and welcome. This will be the first video of this series. In this video, we will have an introduction to radiology, and we'll talk about atoms, electromagnetism, and the discovery of X-rays. So my question to you first is, what do you know about radiation? I'll give you a second to think about that. Some things that may come to mind is it's dangerous. It's it comes from nuclear reactors. X-rays are radiation. We as radiographers know it may be used to create images. In this lesson, we'll talk about those things and more. Okay. In this class is the introduction to the science aspect of radiology. In this class, we will expand your base knowledge of radiation in both the concept that you already know and adding new concepts. So we may go slightly beyond what is needed at times for our purposes in order to gain a complete understanding of the material covered throughout the lessons. In this lesson, some things will be basic. Maybe all things will be basic to you. Some things you may not understand at the moment. Don't be discouraged. We will touch on a broad range of topics that will be explored and expanded upon later. With that, your number one resource should be your textbooks, whatever you were assigned through your studies or in your schooling, and your professor or your instructor should be your go-to resources for information. Don't rely on these PowerPoints for your main source of information. Use them only as a supplement, okay, for your information. Okay, so we'll start with numbers. In science, numbers are important for describing the scale of what is being described. So much so that a number is referred to as a scalar. When it has a direction, like in science, it can be called a vector, okay? But when it's just a number by itself, it's referred to as a scalar. But we won't use those terms for our studies. But with this, when describing phenomena in nature, the scales of numbers can become difficult to recognize and or distinguish. The example is these two numbers below. One of the numbers above is 10 times the size of the other number. Just look and say which one. Maybe you can tell which one. If this was referring to the size of a muffin, you might be very shocked or disappointed. Okay, this is why scientific notation is utilized. Okay, so in scientific notation, the number on the left is the 3 times 10 to the negative 15, and the number on the right is 3 times 10 to the negative 16. With this, you can tell very clearly which one's larger here. Okay, the one on the left is the larger number, so this is the one that's 10 times the size of this one. The 10 to the power, x-axis said as 10 to the power, 10 to the 15. When the x-axis is negative, it moves the decimal point that many places to the left. As in this example, there's many zeros, so this is a very small number relatively. And there's a negative, as you can tell. When positive, it moves that many places to the right. So if this was a very large positive number, it would be, or if this was raised to a positive, a high positive, it would be a very large number. All the places that don't have a value assigned, zeros fill into place, and that's true if with the decimal or without the decimal. Next next we'll talk about units, and we'll just do a little bit of basic math. A number is essentially useless without a unit attached to it. The example I give is 7. 7 what? What does that mean? Well, 7 chairs. Okay. Now we have an idea of what the scale of 7 is referring to. 7 chairs. Having the correct unit is important in order to answer the question. We have 3.14, it could be meters, it could be centimeters, both a measurement of length, but completely different results. And again, these two are a scale of 100 difference, so a meter is 100 times longer than a centimeter, and again, referring to the muffin, so if you were just, it would be 100 times larger, right, depending on the unit that is being used. Or more, it could be 100 times more, larger. Some basic math units. So when you multiply 2 units together, it could be squared of the same unit. So a meter times a meter makes a square meter. Okay. A meter divided by a meter is a unitless value. So the meters cancel. If you have the same value on top and on the bottom of a when you're dividing, they cancel each other out. It's the same with units. So something like a kilogram meter divided by meter would equal kilogram. The meters would cancel out. The kilogram would remain. Another aspect is a meter. So something raised to the -1 power will equal the same as like the inverse of it, so it's 1 over meter, okay? And that continues for a unit or value to the -2 power, so it would be 1 over the value or the unit to the second. If you feel like you need to review some math concepts, it's encouraged to throughout your studies. Math may be used to help enhance the lecture and to get a broader understanding of the lecture. So it will be necessary to know some basic math. Okay, so now we're going to go on to atoms and atomic structure. All right, and we'll see, and we'll learn about this here. Okay, so we'll go ahead and we'll talk about the atomic structure. What makes up an atom, and what is an atom? The nucleus is made up of protons and neutrons. Okay, in an atom there's also electrons, and what is now described as like a cloud around the nucleus. A proton has a positive charge, an electron is negatively charged, and a neutron has no charge at all. An atom is mostly made up of nothing. So the nucleus is in the center of the atom, and with the electrons around the cloud, the spaces in between make it so that something like hydrogen is this number, 99.9996%, okay, empty space. So it's highly empty space. So only that 0.00004 will be is made up of something in a hydrogen atom. This is a good example of why scientific notation is an important thing to utilize. So now we'll talk about atomic number and atomic mass. The atomic number of an atom is what element it is. This is set by the number of protons that the atom has. For example, hydrogen has 1 proton. If it had 2, it would not be hydrogen anymore. It would be helium, which is the second element. Okay, so the element number and what determines what element it is the number of protons that an atom contains. So the atomic mass number is the number of protons and neutrons added together. For example, if an atom has 6 protons and 8 neutrons, the atomic mass number is 6 plus 8, which is 14. Okay, and this element would actually be something known as carbon-14. Okay, which is used for like radioactive dating. Okay. We'll talk about notation, and as you can see here, the standard notation for describing an atom is in this format. There's a superscript A, a subscript Z, and then an X plus minus. We'll talk about what these mean here. A is the atomic mass number, so the atomic mass number goes in that slot there. The Z is the atomic number, which again was determined by the number of protons. X is the element, what element it is, the element symbol, which is done by letters, and the plus minus is the valence, okay, which is the charge of the atom. So for example, this would be lithium here. We know it's the third element by the 3, which is the Z number there. We know that there would be 4 neutrons because the atomic mass number is 7. So the number of protons minus the atomic mass number minus the number of protons gives us the number of neutrons, okay? And we see that there's no charge on it, so that means that there must be 3 electrons. So the number of protons, which are positively charged, equal the number of electrons, so which are negatively charged, so there's no mass. We just add the how many positives there are, how many negatives there are, okay? So if it lost 1 electron, then it would be more positively charged, because then there would be 3 positives with the 3 protons, and there will only be 2 electrons because it lost 1 of the 3, so there's only 2 electrons, so 2 negative charges, and that would make a 1 positive charge, so we would just put a little plus symbol up there in that spot if that was the case. Okay, so on this next slide, we'll go ahead and we'll talk about some elements of interest. Okay, some elements of interest in radiology. Some you may have a idea of why they're interesting. Well, we'll explore them later in other lessons, other videos. But the elements of interest in radiology are Pb, the symbol for lead, which is 82, tungsten, barium, iodine, iron, calcium, aluminum, and carbon. And you can see that they're what they look like, okay, in their raw form on the right there. So now we'll talk about atomic shell. Okay, the atomic shells and binding energies. So we're talking about the electrons in in this slide, which travel around the nucleus and are in different shells. So the electrons travel in what we call different shells around the nucleus. The shells are labeled with the letters starting with K, which is the closest to the nucleus, and the next closest is L, then M, then N, and so on. With this, the closer to the nucleus the shell is, the greater the binding energy of that shell. The actual binding energy of the shell depends on what element it is, okay, with larger elements having higher binding energies. And here's some examples here. Example of the K shell for like carbon, which is element number 6, is 0.03 kilo electron volts, okay, so that's the amount of energy, which is just like 300 electron volts that the K shell electron has binding with the atom. And then moving up to something like barium has 37 keV, okay, so that's 37,000 electron volts that the K shell electrons are bonded with in barium, and then tungsten is 69.5 keV. And then as you come out, okay, so like the L shell, so in carbon we go from 0.3, and then it goes all the way down to 0.001, which is 10 kilos, so it goes from 300 to 10 from the K to the L. So as you go farther out with the KLM, the binding energy becomes less, okay? Tungsten goes from the 69.5, and then it goes to 12.1 for the L shell binding energy of tungsten. Okay, so we'll go on and we'll continue with the atom, and we'll talk about the model of the atom and how it's changed over time. So a model is something that we utilize in science that allows us to work with complicated issues. It may not be exactly what is actually happening in reality, but it is a way that we can work with the atom or whatever we're working with, and to allow us to perform what we need to do. Okay. So as our understanding of nature of the universe has become accurate, so has the modeling of the atoms. For the materials covered throughout the radiology courses, the Bohr model is what will be utilized. Okay, and we can see here through time how how the atom has evolved. In the 1913, the Bohr model is the one that we're going to use, where the nucleus is in the center. Okay, you can see that it's positively charged because the only thing there is protons and neutrons. Neutrons have no charge. Protons are positively charged, so there is a positive charge in the nucleus, and then the electrons around, and you can see the shells around. Okay, the more accurate one now, as mentioned, was the cloud, but for our purposes, this model doesn't allow us to work with it in a way that we need to. So from now on, the Bohr model is what will be utilized. So we'll go ahead and we'll talk about the structure of matter. Atoms can combine together to form what we call molecules, and you see the word molecule just floating out there right now, a preview of things to come on this slide. But a molecule is two or more atoms bonded together. A compound is two or more elements bonded together. Okay, so all compounds are molecules, but not all molecules are compounds, and we can see it here. The element, which is in the top left here, is atoms of element argon that exist on their own. Okay, there's no bonds between them. And then here there's oxygen atoms, which join in pairs, and this would be a molecule. Okay, so it's two or more atoms are bonded together. Okay, is just the definition of a molecule. A compound is two or more elements, so the element of carbon, the element of oxygen are bonded together here, and that makes a compound. There are two different elements that are bonded together. Okay, we don't need to worry about mixture for our studies. Okay, so we'll go ahead and we'll talk about the bonding. We mentioned bonding on the last slide, about how different atoms can bond together, and they can bond together with different elements. So we'll talk about that. So there's two different ways that atoms can bind together. The bonding of atoms can be either the covalent, and that's where they share electron or electrons between themselves, or they could be ionic, where they give up an electron. Okay, or it could be multiple electrons, I believe, in both these cases, and the other one takes the electron. So in the example here, we see that the sodium atom gives up to the chloride atom one electron, and this orange electron here goes over here, and that's referred to as ionic bonding here. where the oxygen and hydrogen, and this of course would be like water. This is how water would bond. It's like a covalent bond, and it is sharing the electrons here. Okay, so they're both sharing these electrons. Okay, and the covalent. I like to think of covalent as like co-worker would be a good analogy. So like covalent, co-worker. You're supposed to work together, so you're sharing the electrons together, and the covalent bonding. Okay. So now we'll go ahead with our lesson, and we'll talk about electromagnetism. There's fundamental forces of the universe. Okay, the four fundamental forces of the universe include the electromagnetic field, the strong nuclear force, weak nuclear force, and gravity. So one we're very familiar with already, which is gravity. Okay, we know how to manipulate it, and we understand it very well, that it keeps us planet the Earth. It makes things fall, okay, towards the center of a mass. The other ones we might not be so familiar with. Okay. So gravity, obviously, with the falling of the apple to the ground. Electromagnetism, the strong force, which keeps the electrons bonded to the nucleus of an atom, and then the weak force. So these two are nuclear. So nuclear typically refers to as the atom. So the strong and weak force. We will be using the strong and weak force in different ways. It won't be explicitly said, but electromagnetism is what we're going to focus on for our studies. Okay, focus beyond the electromagnetic field. With that focus, we will take a little step back, and we'll just talk about waves in general. Okay, so waves are an oscillation through a medium. Okay, they are modeled, okay, on a sine wave. They can oscillate at different frequencies. The peaks of a wave are known as crests, and the valleys, or the lowest points of a wave, is a trough. Okay, the height of displacement of a wave from the zero to the highest point, to the peak, is known as the amplitude of a wave. Okay, the distance between one full cycle, sometimes called the period, so is the wavelength of a wave. Okay, and we can see the example here of the things we were talking about. Okay, so the amplitude. So let's start with the amplitude. Okay, so the amplitude here is how far the displacement is from the zero. So this would be like the zero line all the way up to the very peak. Okay, the highest peak is known as a crest. Lower peaks are known as trough. Okay, and then the wavelength is the distance of one full cycle. So one full cycle is when the wave goes up to its peak, through the zero, down to its lowest valley. So it's experienced the peak and the low. Okay, and it's back at the zero. Okay, if it starts at the zero, it's back at the zero. If you start at a crest, it's the same idea, where this example is of this wavelength here. It goes from crest to crest. Okay, it can go from any point, okay, to any other point. All right, as long as it can go from here to here. Okay, as long as it's at the same level of displacement. Okay, it could be on the bottom. Okay, even as long as it's at the same level of displacement, it's gone through one full cycle of going through its peak, through its lowest. Okay, then it's back where it started, either at the zero or at its peaks. Okay, this will be called, this will be referred to as a cycle, and the distance, okay, as you can see, the distance here is called the wavelength. last slide, we talked about frequency, okay? Frequency is measured in hertz, okay? After Heinrich Hertz, the German physicist who proved the existence of electromagnetic waves, okay? The unit hertz is 1/seconds, or seconds to the power -1, okay? So it was referred to as per second. So something that we know of more commonly as like per second would be, or per a time would be like miles per hour. Hour is just a measurement of time, okay? So it's how many miles we go over a second, okay? So a hertz is how many cycles an electromagnetic wave does per second. So it's the same kind of analogy there. This is equivalent to 1 cycle per second. If it's 5 hertz, that means that 5 event cycles has gone per second. In a wave, a cycle is 1 full wavelength. Okay, so down here we can see, as we talked about before, the wavelength, okay, could be from the 0, reaches the peak, reaches the bottom, back to the 0. Okay, so this is an isolated wavelength here, or just 1 cycle of a wave. Okay, and this is like a sine wave is the model, all right? But hertz is not capitalized. Okay, so the word hertz, when it's written out, isn't capitalized typically, but the abbreviation is the HZ. So just be aware, you know, if you see that and you're reading more things, it's not miscapitalized, okay, on both ends with the H of the word hertz and the large of the unit, the capital H. Is there anything else we can think of that's measured in hertz? An easy one might be like the radio. So the radio that we tune into, if it's FM radio, is in megahertz. Okay, so something else might be sound. Okay, the tone of a sound is measured in hertz as well. So we're already familiar with the idea of the unit of frequency. Okay, and as we've seen, there is a relationship between frequency and wavelength, and this relationship can be expressed in this equation here, which is V. V is the speed at which the wave travels, okay, in the direction of its traveling, and then F equals F times lambda, okay, and lambda is the length of the wavelength, okay, and F is the frequency in here. It can also be written in a couple different ways, where F equals the speed of the wave divided by the wavelength, or you can also solve for the wavelength. So wavelength equals the speed of the wave divided by frequency. Okay. From the equation, we can see that the greater that the wavelength, okay, so the larger that this number is, okay. So if this larger is number 1 on the bottom of a fraction, okay, the answer is going to be lower, okay. So something like 1/2 is a bigger number than 1/4, right? So so the 4 is a larger number on the bottom, so the frequency is going to be a lower value, okay, if the wavelength becomes larger. Likewise, the shorter the wavelength, the greater the frequency, okay? So these are kind of the back and forth here, okay? So the greater the wavelength means lower frequency. The shorter the wavelength means higher frequency, and vice versa. So if the frequency goes up, the wavelength is going to become shorter, okay? Okay, so now that we learned a few things about waves, we'll go ahead and we'll learn more specifics about what electromagnetic waves are in their properties. So electromagnetic waves are a form of energy that travels through the universe. These waves travel at the same speed, the speed of light, which is denoted as c, 3 times 10 to the power of 8 meters per second, which is like 300 million meters per second. Since we are focusing on electromagnetic waves, c will be used now for the v, which was the speed before the velocity, how fast the wave is traveling. We'll use c from now on, which is the value there. The medium they oscillate through, we learned that waves oscillate through a medium. The medium that electromagnetic waves oscillate through is the electromagnetic field. The electric and the magnetic fields are at right angles to each other, okay, and they are referred to, and this is often referred to as like transverse. So the electromagnetic wave travels in a transverse fashion, okay, which is seen here, okay. So the electric field, which is in red, okay, as you can see, is going like up and down on our page, and this is at a slight angle to help you better see, okay, so it's going up and down on our page, all right, and the magnetic field is traveling like in and out of the page, okay, and the direction of travel is this, okay, so the direction of travel is how fast the wave is traveling, okay, so it's traveling at the speed of light in this direction, right here, okay, not this isn't the speed the wave travels, okay, it's the direction that the wave travels. Is referred to as the speed. They are not deflected by electronic or magnetic fields, so electromagnetic waves are not deflected. They can't be influenced by electric or magnetic fields. So we'll talk about electromagnetic waves and energy. As stated before, electromagnetic waves are a form of energy. The amount of energy depends on the frequency of the wave, as seen in the equation. E, which is energy, equals frequency times h. H is the Planck's constant, okay, and our form of the Planck's constant that we need is equal to 4.135 times 10 to the negative 15 electron volts seconds, okay. The EDS is electron volts times seconds. In the equation discussed earlier and the equation above, frequency is utilized in both. We saw frequency is dependent on wavelength and velocity, and then the frequency can be dependent on the energy, or the energy of the wave can be dependent on the frequency, okay? With this, we can solve for F. In both, we can use substitution to acquire an equation relating energy to wavelength, okay? So we have an equation that relates to frequency, which is an aspect of the electromagnetic wave that we can measure, and then to energy. So now we can also take the wavelength and we can relate that to energy. So if we know one, we can find the other ones, okay? So we do that by E equals F times H. There's the original equation. We divide both sides by H, and we find F. So we're going to substitute this F into the equation before, which is C equals F times the wavelength. We bring the F in, which is the E divided by H from the other equation for the F in this equation. Now we have the equation. This will be better here. Now we have the equation seen here, okay? So we brought this down to this F, now we have this equation, okay? And with that, we can solve for whatever we want, okay? We can use it in this form, okay? Where we have the speed of light equals the energy times lambda, all divided by the Planck's constant. Or we have, we can solve for the energy, equals the speed of light times the Planck's constant divided by the wavelength, okay? So now let's talk about the electromagnetic spectrum. Different waves can be any unique frequency. The electromagnetic spectrum is a range of frequencies that make up the electromagnetic field. The lowest frequency waves we call radio waves. As the frequency increases, we refer to them by different names. As the frequency increases, we may refer to them as infrared, visible light, ultraviolet, X-rays, and then gamma rays. And remember, as the frequency increases, the wavelength is decreasing, okay, and the energy is increasing. Okay, so as the frequency increases, the energy of the waves increase, and the wavelength decreases as the frequency increases. These are all the same waves. They're just a disturbance of the electromagnetic field. Okay, they're just at different frequencies. So these, so we utilize them in different ways, or we refer to them differently. Okay, the reason that we perform different tasks with the different sections of the electromagnetic spectrum is because they have different properties. So a very obvious property that was already stated is that as frequency increases, so as the frequency changes from radio waves to what we call infrared to what we call visible light, the amount of energy that's contained, that's contained in the wave will increase also. So from our standpoint, we can use them in different ways. Okay, that different energy that's contained in the different frequencies of electromagnetic waves. So we'll talk about the electromagnetic spectrum here, and as frequency increases, the wavelength decreases. Okay, and we can see that here, whereas the frequency is increasing, so every step here from ultraviolet to what's more considered in the X-ray category, okay, to gamma rays, each step here with these from 10 to 18 to 10 to 20, that's going up 100 times. Okay, so the frequency is 100 times higher with each of these increments here. Okay, and as we see down here, the wavelength of roughly the same here has gone down 100 times, so the distance is 100 times less. Okay, so it'd be like from a meter to a centimeter is how large of a change is happening with each one of these. Okay, notice that visible light is an electromagnetic wave. Okay, so this is visible light spectrum. Okay, its wavelength is between, it could be 400 to 800, some things say nanometers. All right, this right here is 400 to 750, which is common. Sometimes it's 400 to 700. This number can change depending on the text that you're reading. Okay, this is different because it's measured in a different unit here. Okay, it's measured in angstroms. Okay, but it's 400 to 700, 750, 800 nanometers. Okay, is the visible light. The spectrum for visible light is known by the acronym as Roy G. Biv. Okay, representing red, orange, yellow, green, blue, indigo, and violet. Okay, which is what makes up the rainbow, which makes up all the colors that we see. So everything we see is contained just in this range of frequencies. Okay, which is actually much smaller than what's represented here. Okay, that visible light's always blown up bigger because light is what we know and what we're most familiar with. Okay, so as you can tell, that red is like the longest. Okay, it's the longest, so it wavelength, and violet's the shortest. So red is would mean that it's the least energetic. Okay, it's also the lowest frequency. All right, and then blue is more energetic. So blue light is more energetic than red light. Okay, by whatever degree it could be relevant in certain studies. Okay, so moving on, we'll talk about electromagnetism a bit. An electromagnetic wave has something called wave-particle duality. Okay, this is a model to explain how electromagnetism possesses wave and particle-like properties. Okay, and there's a nice picture down in the bottom right that displays that wave-like. It could be wave-like or particle-like. From the equations below for energy, as wavelength increases, frequency decreases, and as wavelength increases, which is the same as frequency decreasing, the energy decreases. Also, as wavelength decreases, okay, the energy increases. Okay, this change in energy changes the behavior, okay, of waves throughout the spectrum. Okay, the lower the frequency in the spectrum, the more it behaves like a wave. So lower frequencies would be something like the radio waves, right? And even maybe like microwaves, perhaps. Okay, and they behave more like a wave. The higher the frequency, the more it behaves like a particle. So higher frequency ones are like the gamma X-rays. Okay, it behaves more like a particle. And the middle frequencies behave like a wave particle, or kind of like a wave particle, okay, at times. So they can behave kind of as both when they're tested, when the experiments are run on and everything, okay. So this is kind of like the warning that like quantum is weird. Quantum means subatomic, okay, and some quantum things will be coming up later on in the studies and stuff, so just know that when you're talking about it, quantum's weird. For our purposes, the information that's given is the information that we need to know, okay. We'll move on and we'll talk about the discovery, okay, so the discovery of X-rays. Just a side note, in other texts, the term light or radiation is used to describe the entirety of the electromagnetic spectrum, okay. From this point forward, for my purpose, the term radiation will only be used referring to X-rays and gamma rays or other forms of harmful electromagnetism or particles. Okay, we haven't learned about particles yet, but furthermore, the classification terms like radio, UV, ultraviolet, etc. will be employed when the frequencies concerning the term are being discussed. So when we're talking about ultraviolet, I'll say ultraviolet. I won't say radiation as a general term. Some texts or will use radiation as a broad term, or if you're looking at other resources from the internet or other kinds of points of information, they may use radiation as a broad term, okay, and for us, we won't be thinking about radiation as the term radiation as a all-encompassing term of electromagnetism, even though it is not inaccurate to use, okay. So for our purposes, we will only refer to it as harmful rays, okay, which is what we utilize, okay. Light, if I use the term light, it would denote like visible light, okay, the visible light spectrum, okay, because sometimes light can be used to talk about all of the electromagnetism, okay, all of the electromagnetic spectrum, okay. So just be aware that when you're reading even your textbook or other books, okay, how these terms can be used at different times. So we'll talk about the history. Okay, so the well-known discovery of Isaac Newton, okay, and what led up to the discovery of X-ray here in 1665, and a prism was left on the table with sunlight shining in on it, led to the knowledge that light being made up of a spectrum of colors. Later experiments showed that with another prism, the color could be combined into a white light again. And also that one color could be isolated in different ways, okay. So so before this, it wasn't known that sunlight was made up of the colors of the rainbow, okay, which is, as we learned, part of the electromagnetic spectrum. So this was kind of the first discovery that there is such as things as electromagnetism. Okay, there's a picture here to the left, and you can see how the different prisms done in different ways. It can isolate one color, or it can be used to recombine back to white light. Okay. In 1801, the double slit experiment was performed by Thomas Young. This was performed with light and demonstrated the wave behavior of visible light. Okay. In 1830, Hans Christian Ortzen showed that electricity and magnetism are linked together. In 1865, James Clerk Maxwell demonstrated that electricity and magnetic fields travel through space as waves moving at the speed of light. Okay, so way back in 1865, we have that electricity and magnetism, electromagnetic, are linked together somehow. And we demonstrated that the electromagnetic fields now travel at the speed of light. This is a picture of James Clerk Maxwell. Okay, he's called the father of light, you see, and they use the term light again, referring to light speed, but it's also referred to in this instance as the whole electromagnetic spectrum. Okay, so in November of the 1886, the Hertz discovered radio waves. Okay, through designed experiments. Now we'll talk about the how X-rays were discovered. On November 8th, 1895, William Conrad Röntgen was experimenting with a Crookes tube, something called a Crookes tube. So the spelling of Röntgen, this is the German spelling of Röntgen that is here. A lot of times we spell Roentgen, okay, with an E, and that's the more the English spelling. So here it's just spelled with the as this, the German spelling. Okay, this is a picture of him here on the left. He was energizing the Crookes tube in a fluorescent screen a few feet away, painted with the barium cyanide, which is this chemical here, glowed. Okay, it fluoresced, which when something fluoresces, that just means that it emits light. Okay, he found that it could be made. He also found that he could make the screen glow through books. So Röntgen began researching this phenomenon. So this is a unique phenomenon that something can be affected at a distance and also not with direct line of sight. So line of sight would be like a light, okay, how that we can see something, but if something blocks it, the light can't penetrate, so we can't see what's on the other side. But with this energized Crookes tube, something very odd happened where even with a barrier in the way, it was still affecting what was on the other side. Röntgen discovered their medical uses when he made a picture of his wife's hand on a photographic plate. This was on December 28th, 1895. So it's just about 6-7 weeks later, after he first discovered X-rays, that he wrote an initial report on the new kind of rays. And there's a picture of the wife's hand, the famous picture of the wife's hand on the left. X-rays. So in January of 1896, Röntgen sent a letter to physicists around the world discussing its new type of rays. It was said that in 1896, 49 essays and around 1,044 articles about the new rays were published. So it was discovered in November of the year before, and just in the next year, more than 1,000 articles were written about this new type of ray. Röntgen did not patent his discovery. He felt that the work should benefit all. In 1901, he was the first Nobel Prize winner in physics. So through experimentation, Rankin, whose name is now spelled the English way and not the German way here, if you notice, discovered some properties of X-rays. There's 12 here. These properties are still true today. So they include X-rays are highly penetrating invisible rays that are in the form of electromagnetic radiation. X-rays are electrically neutral and therefore not affected by either magnetic or electric fields. X-ray can be produced over a wide range of energies and wavelengths. X-rays release very small amounts of heat upon passing through matter. X-rays travel in straight lines. X-rays travel at the speed of light. X-rays can ionize matter. X-rays cause fluorescence of certain crystals. So the crystal that was out, the barium crystal that was out, fluorescent glowed, okay, when it was being exposed to the X-rays. X-rays cannot be focused by a lens. They travel in all directions. X-rays affect photographic film. X-rays produce chemical and biological changes in matter through ionization and excitation. X-rays produce secondary and scatter radiation. So with this concludes the video lesson for today. I hope to see you in the next